We've all heard that the universe is expanding, but how could we know that by sitting on our tiny planet? The answer lies in a little-known property of electrons in light, and some chemistry and physics. Light is made up of the visible light we're used to seeing, but the electromagnetic spectrum extends past red and violet into radiation we cannot see. We describe light using waves, just like sound. A wavelength is the distance between the peaks of the waves. The wavelength of light also relates to its energy. Shorter wavelengths have the highest energy, which will be important later. Just like Newton did with a glass prism to see a rainbow from sunlight, if electromagnetic waves of many wavelengths are refracted, we can see them all individually. Therefore, when light from different stars and galaxies reaches our planet, we can split it up into the different wavelengths the same way a prism does. But we don't see the continuous spectrum like expected. We see patterns of dark lines. These provide the key to understanding distant objects. These dark lines are called absorption lines. The wavelengths here are absorbed by electrons within the atoms of stars. Let me explain. Electrons can occupy different orbits around the nucleus. Since protons attract electrons because they're opposite charges, electrons with closer orbits have lower energy and orbits farther away from the nucleus have more energy. To jump from close to far orbitals, electrons need energy. We just learned that light has energy dependent on its wavelength. I told you it'd be important. Wavelength of light with a particular amount of energy could be absorbed by the electron, so it occupies a further orbit. It can also emit that same wavelength to jump back to ground state or a closer orbit. Each element needs different amounts of energy for the electrons, since most have a unique number of electrons and orbitals. Therefore, the absorption lines in the spectra can be used as a signature to differentiate between elements. The core of the star emits a continuous spectrum. Thermal radiation is emitted at all wavelengths, and stars are very hot, but the colder gas around it is full of bored electrons. They absorb their designated wavelengths, leaving dark lines in the spectrum. The science analyzing spectra is called spectroscopy. Since every spectrum has lines corresponding to the elements it's made out of, we can figure out the composition of distant stars. But here's the key to the expanding universe. The wavelength of light changes if the object emitting it is moving. Think of it like this. An ambulance zooms by with its siren blaring. The pitch increases as it comes towards you and decreases as it drives away from you. The Doppler effect, as it's called, relates to every wave, including sound and light. Coming towards you, light waves are compressed, shorter wavelength, and going away, light waves are elongated, longer wavelength. When astronomers observed the spectra from objects in space, they noticed the patterns in the absorption lines were shifted towards longer wavelengths, or redshifted. This means that every distant object is rushing away from us. The further the object, the faster it's moving away. In other words, the universe is expanding. Using a small amount of chemistry and physics knowledge, we can deduce the very nature of the universe, all using just a little bit of light.